Yeah, I think it was my idea that I think we can contribute to the Friday seminar. So this presentation is about the wireless communication technology especially for the brain-computer interfaces. Yeah, so first I start with acknowledgement. So this project was funded by ERC. And also I want to thanks for the contribution from my team, 4 PhDs. They are all EE, and then one postdoc that is in the neuroscience background. A bit about myself, although I think they're all colleagues. I hope that it's don't need to take too much time. So I joined IMEC since 2010. I'm currently scientific director. I have ERC grant a few years ago from 2021, and also currently I'm guest professor in Delft University. I'm also steering committee in I5C conference. Okay, so this is outline. First, I will start with the introduction of the brain-computer interfaces, and then I'll also talk a bit on especially on the challenge in terms of the wireless telemetry system. And I would go on to also talk a bit more how we can be inspired from Retina to tackle some of the challenges from the wireless telemetry in this implantable system. There are a few components I will go one by one, and then finally is the conclusion. So first start with the BCI. Brain is considered as the most complicated object in the universe. And we have around 86 billions of neurons, and then each of them has thousands of connections. So it's a super complex network. And actually, we know quite little about it. And there are many technology we try to develop in order to help us to better understand our brain. And most of this technology are imaging based, and like fMRI. And then this type of imaging method has issues is that it cannot really know what is exactly happened. So it is a bit similar to like we want to use a telescope to observe the universe, try to understand the universe. But then when you see it does not have a good enough resolution, either temporal resolution or spatial resolution. So I think that's the reason that we try to send rovers to the Mars, and then we try to take a lot of high quality image, and then wirelessly sending back to the Earth for the analysis. So actually, we are also doing the same thing to try to understand our brain. We have this kind of intra-cortical sensors. They are going to be insert to the brain, to the cortex, and then you can record the electrical activities of the single neuron. And this kind of intracortical sensors, one example that is FDA approved is this kind of Utah array. That has lots of needles with electrode, and then they are going to be inserted to the cortex, so you can really record the firing of the neuron. And BCI, the brain-computer interfaces, the definition was on the ChatGPT is a communication pathway between the brain and electronics, and it was introduced in 1970s from UCLA, and then in 1990s, 20 years after, some scientists from Berkeley, they tried to put the intracortical sensors for the brain-computer interfaces, and then realized this kind of intracortical sensors provide very, very good recording and also decoding quality. So recently, BCI are demonstrated in many therapeutic uses as a prosthetics. So one example is the motor BCI. The motor BCI that can help. That is developed to help to restore the movement. And one very famous project is the called BrainGate project that was funded by DARPA, and then they demonstrate that there was a lady, she was paralyzed due to the stroke. And after 15 years, she was able to use her thought and then use a BCI, and then she was able to control the robot arm, and then she can drink the coffee. So that was at the time very inspiring. There are also other example. That is a speed BCI. So at Stanford University, they also demonstrate that we can use a BCI to translate the thought from a patient who cannot speak, and then they are typing on the screen. So there are also many other different therapeutic example. And here I want to show you this BCI, the intra-cortical BCI, is a very powerful technology that can potentially help many patients with neurological disorders. But they also have, at the same time, has a lot of technology challenges. So here, this slide shows the evolution of the BCI technology in the past decades. So you can see there are too many important trends. So first is that it's becoming less and less invasive. So it's starting from this type of head mount device as a BCI, and then connect to with a long cable connect to the computer. And then at the time, it was able to record around 100 channels. And then a few years ago, the same university, they show again the wireless version of it. And a few years back, they can now record 200 channels. And currently, there are many several star companies. One famous one is a Neuralink from Elon Musk. They try to build up a fully implantable version of the brain-computer interfaces, and they are aiming for recording more than 400 channels or even 1,000 channels of the recording. So from this evolution, you can see it become less and less invasive. So from the head mount wire device to a fully implantable wireless device, wireless BCI. And wireless is a very critical part to make this kind of BCI more clinical viable for humans, because if there's a wire penetrates through the skin, there's a very high risk of infection. So that's wireless is an important part. Also, we want to make device smaller and smaller, so you have a less risk doing the surgery. And the second trend you can see is the number of the recording channel is keep increasing. So from 100 channels to thousands of channels, and that is mainly because we have many neurons in our brain, and then the neuroscientists want to record more neurons and then to improve the BCI performance. So this is a quotation from a professor in UCLA. They say everybody always wanted more neurons, although I think this is likely for neuroscientists. But also you can see the survey from a lab from Stevenson, and then they try to show that the number of the neurons that can be simultaneously recorded is from the past decade almost double every 6.4 years, and then this trend is still continue and even speeding up. I think one of the reasons is that there are many high density either silicon probe or flexible probe was introduced. One example, very famous one is our IMAX NeuroPixels, and then we try to use advanced semiconductor technology to increase the density of the probe, and then the number of the sensing channels is also going up to more than 1,000 channels. Okay, so now we know about intracortical sensors, but when we want to record neural activities, this kind of intracortical sensor is also recording the signal called extracellular signal. It means that you are recording the neuron and you are recording the activities of the neuron next to them. So here is one example of the extracellular recording. The waveform example. So x-axis is the time, and y-axis the channels. And then here you can see this is the time when the neuron is firing. We call spike. And it's important to know that each neuron firing will be recorded by multiple recording channels, and also that means also each channel you're going to record the firing from multiple neurons. And it is important to afterward for the post-processing, we try to separate the spikes from different neurons from the same channel. So we need to keep the waveform feature of the firing as high fidelity as possible. So that means we will need to have a high resolution ADC up to, let's say, 10 bits. Also, the neuron firing, the spike is very sparse, it's very narrow, it's in the order of hundreds microsecond. That means we also need to increase the sampling frequency of the ADC up to tens of kilohertz. So that means that this is easily, you can generate a large amount of data from each recording channel. So yeah, this is what this shows here. Each channel, you're going to record the spike waveform from different neurons. Okay, so then next part, I would like to talk about the challenge on the wireless communication part, why this is a problem when we design a wireless system. So in the previous slide, we talked about to record a spike, we need to have a high resolution ADC, high sampling rate ADC. And at the same time, we also want to increase the number of recording channels approaching to more than thousands. So this can easily do a quick math. It will show that we need a data rate, wireless data rate up to 450 megabit per second at least. So this is a data rate that is pretty high, and then it just try to give you an idea. If you try to now measure your Wi-Fi speed, this is the record that I get. I think if you can reach 300 megabit per second, is already pretty high. And then now we are talking about similar data rate, but now we are going to handle it with a very tiny implants. So they will create a problem. That's the tissue heating, because if you constant power of the electronics, a very small area that's going to heat up the tissue. So in one of the literature from Gasolier, their work showing that they try to show this, they simulate the temperature rises of the electronics or ASIC when they implant into the tissue. And then they try to estimate the temperature rises. And then this is the result they find out, and then they conclude that the temperature rises is heavily dependent on the area and also the power consumption of the ASIC. If you have a higher temperature, a higher power consumption, then you have the temperature will increase more or a smaller area. And then if it's higher than 1 degree, then there will be issues of you're going to damage the tissue. And in most of the cases, in this kind of implant electronics, the wireless communication part will dominate power consumption and also the area. So a general design guideline is they try to design a implant electronics that with a heat flux that is lower than 400 microwatt per millimeter squared. So this already give you an idea that it's going to be very power constrained if you want to design a wireless communication system, a chip. Okay, then another challenge that is about wireless communication is the tissue damage or form factor. So so I will start with this tissue cross section around the brain. So here you can see this is a cortex, and then there's a layer of the tissue called dura that is cover the brain, kind of protecting the brain. And then above that, there will be our skull, bone, and then finally is a skin. And if you want to implant such kind of intra-cortical neurosensors, then unfortunately we have to drill a hole on the skull. That also means that the smaller the electronics, the smaller hole, the less the invasiveness. And then we implant these intracortical sensors, and then we will need to have several wires that is connected to a cranial implant to route the signal. And then this comes comes with another problem because our brain has a relatively micro motion relative to the skull, and then that is coming mostly, for example, when you are breathing or when you are moving your head, your brain is going to move, and then if there's a wires connected to them, it's going to create strain or stress to this kind of intra-cortical electrode. So this paper shows that if there's a micro motion and it's pulling the electrode when they insert in on the cortex, and it will activate glial cells. And glial cells is kind of protecting cells inside the brain to protect the neuron. But then if you have something moving, then it will activate this glial cell. And this glial cell is going to encapsulate the intracortical sensors. And then even just over a few weeks, you will have a very severe degradation of the recording quality because it's going to be covered by the glial cells. So that's why many literature suggests that it's better to design a intracortical sensor that is free floating, so no wires, totally wireless, and then this way they will minimize the activation of the glial cells. Okay, now enough about the challenge of the wireless communication for the BCI. Now we are going to talk a bit more. How can we? Is there any way that we can tackle such a challenge, very stringent challenges? So I would like to start with a retina because a retina is actually quite smart than what we think. It do a lot of amazing things. So a human retina is equivalent to a camera with 100 megapixels. So it's a very high definition camera. Also, it has a very high dynamic range. We can cover this. Our retina can cover a light condition from very bright sunlight to very dark room. So I would like to give you a dynamic range of 20 bits. Our retina can also capture very fast moving object in the millisecond level. So here I give the frame rate or sampling rate of a retina equivalent to 500 hertz. So if you do a quick calculation, it's 1000 gigabit per second. And this is a super huge high data. And then this is a kind of need to be handled by this tiny retina. And then because this data is going to be video data or image data is going to be sent to the backside of our brain called visual cortex through a very tiny optical nerve, this optic nerve. And then they only consume very low power because a whole brain is only 20 watt, and then this power consumes just milliwatt. So there's a lot of things that we could learn from our retina, how they handle this big data and transport them to the other part. So let's look at some numbers. So here, let's say this is a retina. We have we already mentioned we have around 100 megapixels of the data, and then if we do the calculation, it's an analog input. So we take a sunlight, and if we do equivalent data rate, it's around 1000 gigabit per second. We already do an estimation before. Now this data is going to push to this optical nerve, and optical nerve is actually having only around 1 mega of the nerve fiber, and then it's propagated in the form of the spike, this digital bits, and then our firing rate of the this kind of fiber, nerve fiber, is in average 10 hertz, 10 bits per second. So that means equivalently you have a data rate of like a 0.1, like a 10 megabit per second. So if you look at the data rate, it's actually having a compression ratio in the order of 5. So it's a huge amount of compression. And then this is actually already since 1961. The scientist called Barlow, he already tried to have a hypothesis, and his hypothesis is saying that the optical nerve is actually the information bottleneck of the whole visual system, and our retina, they try to do very good smart encoding, so they can maximize the information while with minimum neural cost. And here the neural cost is actually about the bit rate. So these are firing rate times fiber. That is this 10 mega. They try to minimize that so they can reduce the energy consumption. This is this kind of efficient coding hypothesis. Later, many neuroscientists try to follow up, and then it become a theory. There's even an equation that try to describe this hypothesis, try to describe information, and it's also become one of the most successful hypothesis or theory in the neuroscience domain because it helps to explain many things that retina process the image information, and even there's many inference or modern image processing or even communication. So the more the neuroscientists study this, the more they find out the retina is actually much smarter than the just compression. So this is this research is still ongoing. Many neuroscientists still try to study retina, but in principle, the retina, the secret recipe that retina try to make the best balance between the communication and computation is actually having several components that I will try to cover today. So we have actually neural filter. So we try to drop the redundancy as much as possible without losing the important information. We also try to perform certain feature extraction so we can make the processing more selective. On the communication side, we will do multiplexing, and it's more like serialization. And then finally, when our retina transmit the data with impulse. So it's an impulse transmission to minimize the transmission energy. So in the following slides, I'm going to just cover one by one. In the first part, I would like to start with the impulse transmission. So coming back to the how neuron sending the information, they send the information with a spike. And then typically we consider spike as a kind of digital bits. But actually, neuron is not trying to send out bits. They try to send out time information. So this is a quite important part. This important property of the impulse transmission. So if you look at our modern digital wireless communication, typically we can categorize this modulation in two types. One is called continuous wave modulation, and another one is impulse modulation. In continuous wave modulation, we have a carrier frequency, let's say 2.4 gigahertz, everybody knows it. And the data is modulate on top of this carrier frequency. Either you modulate the amplitude, or you modulate the polarity, or you modulate the frequency. If you look at the spectrum, it's relatively narrow. So we also call it narrowband communication. If we look at another type of modulation, is impulse modulation. You try to send the information over a very, very short period of time. And in the just nanosecond level. And then you modulate the information either in time domain or in polarity. So if you look at spectrum, it's relatively wide. And if you are familiar with the wireless communication capacity theory from Shannon, and you will know that wireless communication is actually quite a lot of them about how to balance between the energy efficiency and the spectrum efficiency. And this is exactly two different properties that you will see. And important thing is that for impulse communication or impulse modulation, you can achieve very, very good energy efficiency. You only send the information over short time. One criteria is that you need to have sufficient bandwidth available. So that is a criteria for the impulse modulation to achieve very good energy efficiency. So let's look at a few examples that which we can use this time information transmission to maximize the energy efficiency. So this paper, they try to demonstrate that you to use impulse radio to send out time information to blueprint sensor. So they have this sensor front end first convert the analog value or amplitude value into pulses with different pulse widths. If you have a larger amplitude, then it has a larger pulse width, and vice versa. And then they use the impulse transmission to indicate the start or the stop of the pulse. In this way, they can be very efficient to transmit the sensor information because they transmit with time, not the bits. Actually, we also try to develop the impulse radio for implant use case. So a few years ago in ICC, we also try to use the impulse radio, and then we try to play with the time delay to increase the bandwidth or to increase the data rate. in efficiency, and that was quite successful. But then there's still a limitation is that for impulse radio, if you want to use an implant condition, you probably know that antenna has is a special trade-off that if you want to use a bigger bandwidth, your area will be bigger. That's due to the proportional to the wavelengths. So this is a property of antenna. That means that if you want to use impulse radio, you need wider bandwidth. Wider bandwidth, that means your antenna will be difficult to miniaturize. So this has become one of the limitations that we have, that even when trying to miniaturize them, these antennas still be quite dominant size. So we start to look for other alternative, and one inspiration is, again, we can look from how our nervous system propagate information. So you probably remember the basic physics about ionic current. So if you apply 2 voltage in the salt water with 2 electrodes, the ion with positive charge is going to flow to the electrode with lower voltage, and the ion with negative will flow to the high voltage, and then this will create ionic current. And this is exactly how our nerve propagate the information. They propagate with ionic current. It is pretty fast, and then that has apparently a pretty large bandwidth. So we try to study this property, and then we do a lot of experiments, and then indeed we find out our tissues actually has a pretty large bandwidth, and then we use this property to design a impulse body coupled transmitter. So this is what we demonstrate, that we design this impulse body channel communication, that we are able to achieve like 1 nanosecond of the pulse width, that indicate very good time resolution. Also, we don't need to use a large antenna, and we only use 2 small electrode, and then that is 4 times smaller than typical ultraviolet antenna. And also it's very efficient. It's just a few picojoule per pulse. Now we are trying to build up a bigger system. We try to demonstrate that can we use this body channel impulse transmission to design a free-floating implants. So that's as shown here. So if you have 2 devices, and then you can cut the wire and then send the communication data by this body channel impulse radio, then you can achieve a free-floating condition. We also find out it's very important to also consider in the wireless powering, because if you have a free floating condition, you don't want also wires to provide the power. So we look at the wireless powering, and in this case, we use the ultrasound as a powering modality, and also this year in ICC we also demonstrate this ultrasound powering for this kind of free floating taserless wireless link. Okay. That's the first component of the Retin-inspired application. And second part, I would like to talk about the neural filtering. It's also about the how to reduce the redundancy. So I would like to start with a model called nonlinear model that was presented in already 1973 to kind of model the behavior of our retina. And the linear part means it's a filter. So there's a spatial filter. There's also a temporal filter. And the nonlinear part is this nonlinear spiking model function. And in this slide, we will focus mainly on the temporal filtering and also this nonlinear spiking. If you look at this temporal filter, this is a kind of step response. Then you will probably guess that its functions is very similar to differentiation, or we call delta modulation. You subtract something from the past. So this means that our retina is actually only sensitive to something change. If it's static, it does not respond much. So it only responds to something change. So this helps to greatly reduce the redundancy. And the nonlinear firing part can be modeled with a rate encoding. So if you have a higher input value, then you fire faster. And if you lower input value, then you fire less frequent. And if it's lower than 0, then you don't fire. This is where the nonlinearity comes from. So if you have this property, then you can pretty nice describing the behavior of the retina. So here, put one example. If there's a fly flying through the retina receptive field, when it's and this is a output response of the retina. There's an output cells called ganglion cells, and two types of ganglion cells, on and off. So when the fly that is fly in this receptive field of retina, your on ganglion cells is suddenly fire very fast, and then you slow down. And when this fly away, this is a receptive field, and then this off cells is going to fire fast and then slow down. So this is the behavior of our retina. So and such a temporal filtering and a nonlinear spiking can also be applied in the our camera system. So in 2008, the group in ETH, they also tried to mimic such retina encoding into the camera. They call dynamic vision sensors. And this is how this sensor image look like. They only respond something when there's a changes. It helps to reduce quite a lot of data size from the camera, and also you have a very good, very low latency. And when you look at this image, you also find it very interesting is that even this is the image that our retina send to our brain, but our brain has no problem to reconstruct to a high resolution image that we think we see. So this is the part that is amazing part of our brain reconstruction. So now the question is that can we apply the similar concept also to the extracellular recording, extracellular signal from the intra-cortical sensors? So let's say if we start with the more traditional sampling, we call frame-based sampling. So this frame-based sampling has a fixed clock rate. And then each clock, you're going to provide multiple bits that represent the amplitude value. And if we do the delta modulation, or here we call event-based sampling, you don't need to really have a clock. You only output a binary value when you see large enough changes. You can have a two output, one indicate going down and one indicate going up, just like on and off ganglion cells. And then such kind of event-based encoding or delta modulation is very suitable to apply to the extracellular signal, because our extracellular recording is also is a very, very sparse signal. So in average, our neuron fire like 10 spikes per second, and each spike is just hundreds microsecond a time. So it's a very sparse, and if you apply such a event-based sampling, delta encoding, then you are able to reduce the data by 10 to 1,000 times. And very important is almost lossless. And you don't need to also have a lot of buffering, like many compression algorithm needed. So this is the analog seminar. So I try to cover a bit on the circuits. So such a kind of event-based encoding can also be implemented in the circuit domain. So the DVS camera, they have this event generator. First, they have this photo detector, and then that's mimicking the photoreceptor of the retina. And then we also have a differential circuit to mimic the retina that is performing temporal filtering. And then in the output, there are two comparators that either showing on or off. That is mimicking also the on ganglion cell and off ganglion cells. Also, there's a special type of ADC called level crossing ADC that is also doing similar event-based encoding or delta encoding. So I will not go into detail, but it's actually very similar to the SAR ADC, but just a slightly different feedback path. Okay, so we recently tried to prove this concept by implementing a chip that we can do this delta encoding over 128 recording channels. And we have a quite exciting result that shows that with this encoding, even with a lot 128 channels, we are able to compress the data by roughly 11 times. And this 11 times already include many protocol overheads. And also the high firing rate from the high density probe. And then after reconstruction, you can see the curve, the solid curve and the dash curve, they are represent the loss is very low, and also this is showing the reconstruction from total 128 channels. Okay, so next part about the multiplexing is actually performing the serialization. So like we previously mentioned, the retina need to reduce the number of data because there's a very limited number of fibers available. So that means that you need to perform kind of multiplexing. So if you look at the intra-cortical recording, it's also similar. If you want to have high number of recording channels, you have to do kind of multiplexing. Otherwise, it will be very similar to this experiment that was performed for the primates recording. They try to record. They try to send out the information from 1,000 recording channels. Then this is how it looks like if you want to wire in this so much channels. All of the wires will become very complicated, and then this is likely not going to be clinical viable. So we have to do kind of multiplexing or serialization to reduce the number of wires to just a few wires or even just one, so we can use one antenna for the wireless transmission. Also, make sure that serialization typically also consumes quite a lot of power. We have to make sure this power consumption is low enough, not introducing the tissue heating. So again, let's come back to look at what is a standard approach that is typical now used in the electronics, standard electronic system. So if we have a frame-based sampling system or sensors, then many of the systems use this kind of time division multiplexing. This is a standard approach. So by using this time multiplexing, we can reduce the number of wires. Again, I want to use the NeuroPixels as example. So NeuroPixels has total 384 recording channels, and each of the channel has more than 10 bits. If we try to wire all of the ADC bits out, it's going to be thousands of wires, and it's again not very suitable, not very practical. So actually, they perform this NeuroPixel perform time multiplexing, so the output is only few wires, so they make the system very compact and also more suitable for the potential implant use. But there's a potential downside is that for such kind of time multiplexing, especially if you want to multiplex with a high number of the ratio, then you need to prepare first a very high frequency clock. And then you need to sequentially scan each of channel and then sequentially sending out. And then alignment between them, a synchronization between them, also make the system very easy to consume high power consumption. So now let's look at another system that we previously described that we can use a delta encoding to convert the analog value or value into a synchronous event. By doing this, we are able to reduce larger amount of bits need to be transmit because information is in time. But this is also make the time multiplexing, the standard time multiplexing is difficult. So that's why there was also a protocol called address event representation was introduced in 1999. So the idea is that if you have a lot of channels that you want to do the channel that are coming from the event-based sensors, they provide a synchronous event and you want to do the multiplexing. What you need to do is that you just, when the events come, you just indicate which channel has that event. So that's you represent the bits with this source address. That's called address event representation. And it was quite popular method nowadays is used in lots of neuromorphic computing systems. Again, it's a good protocol, but there's also a limitation if we are talking about want to do it with wireless communication. First is that if you are going to do a high multiplexing ratio, that means your address length will be long. So even just one event, you're going to attach a very long address, like NeuroPixel 384, you need 9 bits address to represent just one event. So it's a pretty big overhead in terms of the protocol. Second is that typically they are not designed in a serial format, and there's no really synchronization is pattern there. So that's also not good for the wireless communication that for the synchronization. So so in our recent design, I want to show a few examples that we have. So first is that we try to develop this serial form of AER for the wireless transmission. So if you have events, let's say up event and down event, first you can attach the address. In here is just 2-bit address represent there are 4 channels, and then 2 bits represent their source address, and then you have another bits indicates either up or down. And then you do the Manchester coding, because the Manchester coding is also helping on the synchronization. You make sure if there's a long 1 or low 0, each of 1 and 0, you always have some transition in between. This is helping to avoid the issues when there's a long 0 or long 1, you don't know how to synchronize. Also, we do the ternary coding. The ternary coding means that you have extra states on top of 1 and -1, you have 0 state. That indicate when it's a silence, you don't need to spend energy in the transmission. So this is also very important to save the power consumption for this kind of event-based system. And waveform example, if this is a spike or action potential, this is how we convert to up events and down event with level crossing ADC. And each up or down events will generate a serial AER as shown here. And then we still find that there are many things that can be improved. So we have a second version of it that we just present a few months ago. We group some of the events in spatial or temporal, and also we attach a synchronization word that's helping for the wireless communication. And if you want to know more detail, you can take a look at how we change the protocol, this AER protocol especially for the wireless communication. Okay, so now I'm going to cover the last components of the retina, the balance between the communication and computation. And I found this part is also the most interesting part, that currently there are still many research ongoing. So when we talk about retina, people always think it's more like a camera, a high resolution camera, that maybe you have some filter. But actually, neuroscientists find out our retina is more like a camera with a very small computer behind that. And this computer is perform feature extraction. And in the previous slides, I already talked about the retina has a output cells called ganglion cells. And then neuroscientists find out there are 40 type of ganglion cells, and each of the type of ganglion cells represent one visual features. So that means actually our retina try to extract 40 visual features. And then the question is why do we need to extract so many features? So if you think about the image, so probably we could think of we have RGB, 3 different colors as features, and maybe we have another features that represent the brightness. We only need 4 features to represent the image. But then actually we extract 40 features. It turns out that most of these features are motion feature, and they are very critical for survival. Because if we can extract this motion feature, it can allow us to have a much fast response time. And if you have faster response time, it helps you to increase the survival rate. And that's how we involve. And another reason is also earlier we talked about our retina try to reduce it, compress by dropping the redundant information, for example, use a delta modulation. But it's effective when the image is static. But if you are in the very dynamic condition, for example, when you are running or the bird is flying, all the image is moving, then this kind of neural filter or temporal filter does not really help too much to reduce the redundancy. And then here you will need to rely on the feature extraction to help you to pay more attention to the such kind of moving object. And interesting thing is some animals like birds, they even evolve to have a bigger retina than their brain, because they heavily rely on their visual feature extraction to help them to survive. Okay, now switch back to the BCI part. So we talked about earlier the intra-cortical sensors that they will they will capture the spike from many different neurons, and then we have to separate the neurons, separate the spike, so to separate the neurons. And this is a kind of, we call it spike classification, or some people also call it spike sorting. And this part is actually a pattern recognition. And let me briefly go through a simple pattern recognition. So it's when you want to do the classification, this is example of a classification. If you have a, you know, the weight and the height of the people, then a person, then you will know, you probably can classify them into children or adult. This classification is kind of, you sort the data based on the known label. So it's a supervised learning. You also you could call it a temporal matching. But the question is that you have to know the label. And most of the time we don't know that. That means that is a case that most of the time before the classification, we will do clustering. Clustering is kind of partition the data that has a similar features without knowing the label. So it's an unsupervised learning. We can also say it's kind of template definition. And here is an example. If you have two groups, then you notice that some group has a similar feature, and then another feature that you can create. There are two clusters. Here comes another question: is that when you do the clustering or classification, actually you still need to know what is the feature you can do that. So you need to perform the feature extraction. It's a kind of process that help you to reduce the dimension so you can more efficiently perform the clustering and the classification. So this is exactly the 3 steps that usually we need to do when we want to recognize the pattern of the spike. So in this slide, it's already sketched how you usually process this spike information. So you have intracortical sensors, and you record the spike from the neurons, and you detect the spike, zooming in, you have feature extraction, clustering, and classification. Once you have this step, you know the firing pattern of each neurons, and then you can use that to perform the BCI control or prosthetic control. So now the question is that since the intracortical sensors is implanted, so when should we transmit out the data? So you could choose, so this is a question becoming a balance between the communication and computation. So you can choose to send out the data right after you record the signal. So in this case, you try to send out the raw data. And then this is going to have very high communication requirements because it's going to be consuming a lot of power because wireless communication typically is very power consuming. So this is a not very efficient approach. You can also choose to transmit the data after you perform all of this computation, and then you transmit the result of the classification. And in this way, you transmit much less data, so you save the energy. But the downside is that you will need to pretty large storage space to perform all of this computation. And also accuracy could be potential concern because it's very sensitive to the outlier drift, etc. So if we look back, actually the part that require the largest the computation requirements is actually this clustering step. So because you need to have a large amount of data storage locally and then try to figure out it from the algorithm. So if we can try to avoid this step, then we are able to perform better trade-off between the communication and computation. So this is actually where we can learn from the retina, because our retina pass the information after they perform the feature extraction. So so similar to we don't do the clustering inside the retina. So this is how we do. So once you extract the feature, you directly transmit out. So I also call it a feature transmission. If you do this, you can avoid to have a large storage space that is required in the implant, and also it's more accurate because it's less discriminative. And this is actually very similar to the partition between our retina and brain. Our brain has 180 billion neuron, large storage space, and our retina only perform feature extraction, and the brain perform most of the cluster. And if we compare with the original approach, for example, you do compared to raw data, you can reduce already data by quite large amount. And then also you need much smaller storage space and more accurate compared to you perform auto computation inside the implant. Okay, so finally here I want to show you one example. So again, here is the typical waveform of the spike. You have several polarization area. And then we first use a level crossing ADC to convert this analog signal into asynchronous events, up and down events. And then we use a spike in neural network to extract the features, temporal features. In this example, we use them to extract the peak and valley of the spike waveform. And the reason we choose a spike in neural network is because it's very similar to our biology. So you only perform the computation when there's events. And then finally, we use the impulse transmission and ER multiplexing to send out once we have this, as soon as we have this temporal feature extracted, we transmit out. So this is how we do to minimize the energy consumption. And then you can try to resemble, this is actually very similar to our retina. And then if you're interested, here, this paper can show a bit more. Okay, conclusion. So in my presentation, I tried to explain to you that the wireless telemetry system challenge in the BCI, first is that you want to minimize the area, so they can minimize invasiveness. You want to reduce the power consumption because there's a tissue heating, but at the same time, you want to maximize the bandwidth such that you can access or record more neurons. And then we can try to learn from the biology, and then we try to build a neurotechnology that is inspired from the neuroscience. We also call it neuromorphic engineering. So we can build better neurotechnology to advance the neuroscience. And here are the few components that we already described that we can be inspired from the retina. And the key takeaway is that to transmit time, not bits. And we also talk about a balance between the communication and computation. If you transmit right after the sensor, you are going to consume huge amount of transmission power. And if you do transmit after all of computation, you are going to have a larger storage space and also very sometimes compromised accuracy. And learning from the retina, we can actually transmit in between to achieve a better trade-off between communication and computation. Okay, so that is the part I would like to share with you. I hope that you find it interesting, and you can share with me your feedback.
Yeah, okay, great. Thanks, Jahong. There is indeed room for questions now. If you have a question, either raise your hand or just shout out.